So, Jai Hind everyone. My name is Ritesh Sharma from AKGEC Engineering College, Ghaziabad. So I am taking the subject Fundamental of Electrical Engineering, and in this subjects today I am going to discuss the topic of three-phase induction motor, wherein I am going to discuss the topic of the torque equation and the torque slip characteristic of three-phase induction motor. So let's start with the first the principle of operation of three-phase induction motor. So in three-phase induction motors, we know that when the three-phase stator winding is energized from the three-phase supply, a rotating magnetic field is set up. Okay, we have already done that part in the previous lecture. So whenever we apply the three-phase supply to the stator winding or the stator winding of this three-phase induction motor, a rotating field is set up. And this rotating field is which rotates around the stator at synchronous speed, which rotates at synchronous speed. And the speed is given by NS 120 F by P, where F is the frequency, at what frequency we apply the, and P is the number of poles. So on this basis we decide the synchronous speed NS given by this formula. So it means that the three rotating magnetic field is there set up in the air gap. Now the rotating field passes through the air gap. When the rotating field is there which passes through the air gap, and cut the rotor conductors, and this rotating field will cut the conductors. The rotor conductors are on the rotors, okay, and which this field will cut the rotor conductor which are stationary, okay, and those conductors are stationary because they are at standstill position. And due to the relative speed between the rotating flux and stationary conductor, and the relative speed will be there because the rotating field is rotating with the speed ns and the rotor conductor is stationary, there will be a relative speed. And because of this reason, the EMF induced in the rotor conductor, because of this, called the Faraday law. Whenever there is a relative motion between the two, there will be the induced EMF in the conductors. Okay, and these rotor circuit, the rotor conductors are generally are short circuited. The closed circuit is this, and because of this, the current start flowing in the rotor conductor, and the current start flowing in the conductor. So this is the reason. This is the method we call it how the current is flowing in the rotor conductor. And we know that the current carrying conductor or the current carrying rotor conductor are placed in the magnetic field produced by the stator. Consequently, the force will act on the conductors, rotor conductors, and this force will act on all the rotor conductors and produces the torque which will tend to move the rotor, in a certain direction or in the same direction as the rotating field. Okay, now how we will decide the direction of rotating of this rotor? So we know that the rotor is urged to follow the stator field, that is, the rotor move in the direction of stator field. The rotor will move in the direction of stator field because of, we can explain with the help of Lenz's law. The Lenz's law says that the cause opposes the effect, and the reason why this rotor is rotating is the relative motion, and the rotor will try to oppose this reason, that is called we call it the relative motion. Hence the relative motion will be, the rotor will rotate in the same direction because ns is the speed of the rotating field and nr is the speed of the rotor, and this difference is called the relative motion. When the rotor is rotated in the same direction, when the rotor speed is increases, the relative motion will again decreases. Okay, that means it will oppose this cause. So hence, to reduce this relative speed, the rotor start running in the same direction as that of the stator field and try to catch it. Okay, so this is how the basic principle or the working principle of the three-phase induction motor. Now we can see that when the rotor start rotating in the same direction, it will accelerate in the direction of field. The rotor can never reach the speed of the stator. Is it possible that the rotor can run at this speed ns? If suppose that this nr is equal to ns, suppose in that case there will be no relative motion. So wherever there will be no relative motion, there will be no induction there at all. No inductions, there will be no induced EMF, and hence there will be no current in the rotor conductor. So practically we can say that the rotor cannot attain the speed of rotating field, that is ns. Okay. Now the term is called slip. Whenever we call the speed ns of the rotating field stator field, and the rotor actual, this is the speed of the rotor actually, and this difference is called slip speed. We can call it slip speed. Slip speed. Slip speed. Slip speed, that is ns minus nr. Hence we can define a term called slip. The slip is defined as the ns minus nr upon ns in terms of percentage, that is this terms. So the difference between the synchronous speed, that is of the rotating magnetic field of the stator, and the actual rotor speed is called slip, and it is actually expressed in terms of synchronous speed. So we call it a slip. Now this is a very important term, so that's why we need to cover it. Now next is important that we cover in our topic, the torque equation. So whenever the rotor rotates, the torque will act on the conductors. So let us find out the torque equation. So first of all, the torque produced by three-phase induction motor depend upon the three main factors on which this torque is depend. Firstly, the magnitude of the rotor current. The magnitude of the rotor current means how much current will be there. Okay, that is I2. I2 is the rotor current. Okay. Secondly, the flux which interact with the rotor of the three-phase induction motor and is responsible for the producing the EMF in the rotor part. So flux is very important. So you can say the phi or flux is for the important part which taking place in the rotor torque production. And the lastly or the third, the power factor of the three-phase induction motor, that is cos phi. Cos phi to rather. Okay. So hence, if we combine all these, if you can see that the torque is basically proportional to, if you are not able to see, the torque is proportional to flux, current I2, and cosine of, that is called cos phi 2 or cos theta 2. You can write cos theta 2. And cos theta 2 is nothing but the power factor of the rotor circuit. Okay, that is the power factor of the rotor. Okay, so these are the three important factors on which the torque depend. Now we can see that the flux phi which is produced by the stator is proportional to the stator EMF. So phi is proportional to E1, and hence we know that according to the transformation ratio, okay, according to the transformation ratio, this E2 upon E1, the K is equal to E2 by E1. E2 is the rotor side voltage, it's a per phase voltage, and again E1 is the stator side voltage, because this winding are three phase winding, okay, stator and rotor. So from here you can say that this E2 again is proportional or equal to phi, depending upon the transformation ratio or the value of K. Okay, so you can write this torque equation. In our torque equation, we can write torque is proportional to E2 I2 cos theta 2. You can write in place of phi, we can write E2. Okay. So now the current I2. Now take this one by one, I2 and cos phi 2. So current I2 is defined as the ratio of the rotor induced EMF running in the running conditions, this to the total impedance of the rotor side. So I2, that is I2 can be written as the total induced EMF under running condition, that is S times of E2, because it is under running condition, so slip will take place, upon this is the per phase impedance of the rotor side. Okay, and the total impedance on the rotor side, the impedance is given by Z2, because the impedance is given by the resistance and the reactance, and the reactance eventually is will depend upon the slip frequency. Okay, that is S. So you can say Z2 will be equal to R2 square under root of R2 square plus S times of X2 square. So this is the total impedance, per phase impedance under running condition. Okay, and hence if you put the value over there, the I2 will be given by this. So I2 must be equal to S times of E2, because this, and just put the value of Z2 over there. So you will get the current, the rotor current in this, where S is the slip of the rotor. Secondly, the power factor, you can define the power factor of the rotor side is R2. We know that the power factor is by the ratio of the resistance to the impedance. So resistance is R2, impedance is Z2. So again R2 upon, and impedance Z2 we already defined is under root of R2 square plus S X2 square under running conditions. So you just put the value over there, and this is the torque equation. So how you can find the torque equation here? So torque is proportional to E2, as we have done earlier. This is the torque equation. This is E2 I2 cos phi 2. So torque is proportional to this E2. This is our I2, and this is the cos phi 2, cos theta 2. So E2 I2 cos theta 2. Now this is proportional to this. Now this is the constant of proportionality is here. We have put this constant because since we know that the P is equal to torque into omega, so obviously this is our power terms. So T must be equal to P upon omega here, and the total torque will be given by total power, that is 3 times the power. So 3 upon omega is nothing but the you can say that speed in RPS, that is 2 pi ns into P, that is called these terms, that is E2 I2 cos phi 2, which is given by this. So from this is the constant term, obviously this is the constant term. So you can write the torque equation. Now you can write the torque equation is given as T uh, torque is given by, the torque must be given by, that is a K, it is a constant term, K SE2 square, SE2 square R2 upon R2 square, because so R2 square plus SX2 square in Newton meter. So this is the torque equation or torque formula, you can say, where E2 is the rotor induced EMF, R2 is the rotor resistance, and X2 is the rotor reactance. Okay, so this is the torque formula or torque equation. Now from this equation, from this torque equation, first you can find the starting torque. Starting torque. Starting torque means when your rotor is at standstill position. So when rotor is at standstill, the slip must be equal to how much? Because rotor speed is 0, so slip must be 1 at N, or NR is equal to 0. When NR is equal to 0, obviously slip must be equal to 1 or unity. So here the starting torque must be equal to K times of E2 square R2 upon R2 square plus S is equal to 1 X2 square. This is the starting torque, T starting in Newton meter. Okay. Now let us find out the maximum torque. How much maximum torque will be there? So this is the torque at starting. So it will this E2 is the voltage which is somehow constant. K is again constant. R2 and X2 parameter are also constant parameters. Okay. So you can say the starting torque is depend on R2. So if you can increase the resistance, obviously the resistance increases, the torque must be increases. Now, second point is the maximum torque. Pmax or maximum torque. How much maximum torque will be there and at what slip? So first of all, the torque equation is already, we know that the torque is given by K times of SE2 square R2 upon R2 square plus SX2 square. This is the torque equation. Now you have to find the maximum torque from here. So it means we need to differentiate this dy in with respect to ds, because slip is changing with as an rotor is running condition, the slip is changing. So you can take and differentiate this with and equate to 0. Differentiate and equate to 0. So it means that dt by ds, when we differentiate this, so first function is this numerator KSE2 square R2 d by ds of R2 square plus SX2 square, S square or X2 square minus R2 square plus S square X2 square d by ds of k times first function, which is numerator s e2 square r2 upon denominator का square, that is r2 square plus sx2 whole square, first function का whole square, equate to 0. When we equate to 0, this will become 0, and when we solve this, we will find this the slip is equal to the ratio of r2 upon x2, that is Sm, or slip at maximum torque. So maximum torque is when occur, the slip is given by r2 upon x2, the ratio of rotor resistance to the rotor reactance. This is the condition for maximum torque. So condition for maximum torque, So now it is required that how much maximum torque will be there. So now if you put the value over there, you will get the maximum torque, that is the T max will be equal to k times of s, which is equal to r2 upon x2 e2 square into r2 upon r2 square plus s square, means r2 square into x2 square into x2 square. So this is the, when we put the value of s over there, you will get the maximum torque, and this comes out to be this will cancel out twice of r2 square. So k times of e2 square upon 2 twice of x2, k times of e2 square twice of x2, because r2 square will be cancelled out in Newton meter. So hence you can see that the maximum torque T max is equal to k times of e2 square upon twice of x2. So it means that at maximum torque, the maximum torque is independent of the rotor resistance. So important point is this: the maximum torque is independent of rotor resistance. Means if you can change the rotor resistance, the starting torque will change, but rotor maximum torque will not change. It is independent of rotor resistance. Okay. So starting torque, as we have seen, that it is dependent on the rotor resistance, but maximum torque is independent of rotor resistance. Okay. Now write down, next is the important characteristics which we discuss in this is called the torque slip characteristics. The torque slip characteristics. In torque slip characteristics, we just draw the relation between the torque versus slip, and the formula for the torque is given by k times of SE2 square R2 upon R2 square plus SX2 square. This is the formula for that. Or you can say torque is, if you can remove this constant, the torque is proportional to that. Okay, so torque obviously is proportional to these parameters, that is since E2 is a constant, R2 is again here constant. So you can say that is proportional to S times of E2 square R2 upon R2 square plus S square X2 square. To draw the characteristics, first we divide in two regions. Because slip, when we draw the slip, the characteristics, if we draw the characteristics, this is the slip is taken in x-axis slip, and this is the torque in y-axis. So slip we are varying from at s is equal to 0. Suppose this is the s is equal to 1. Because slip is there from 0 to 1 here. So initially when the slip is 0, the speed must be equal to the rotor at 0 means it is ns, n is equal to ns. The rotor is theoretically it is running with this speed ns, because s is nothing but ns minus nr upon ns. So slip 0 means ns and nr will be same here, and at s is equal to 1, this n must be equal to how much? 0. nr, sorry, is equal to, this we can write nr is 0. Mean this is the position where the rotor is at steady state. Now, so we have we can divide this characteristic in the low slip region and high slip regions. So at low slip region, we can say that when the slip is low, this part, this R2 square is very, very greater than S square X2 square. Means this part will be very, very greater than this, so that we can neglect this part. It means that when we put this value in the torque is proportional to the S, that is slip. It means that when the torque is proportional to slip, it is almost a linear. So if we can see that this is the maximum torque, so you can say that at when the value of slip is low, it is almost linear. Between the torque and slip curve. So at this point, this torque is maximum, and at maximum torque, this is called the slip, which is Sm, which is a ratio of R2 upon X, because at this point of slip, the torque is maximum. So at low slip region, the torque is almost linear. Okay, it will vary like this. But in high slip region, now when the value of slip is almost more, it will increase, it will dominate. So what happens at this point? The S X2 square will be greater than the R2 square. So in that case, we will neglect R2 square comparative to this. So here we will find that the torque will be inversely proportional to the slip. Now the torque is inversely proportional to slip. It is almost like a hyperbola or rectangular hyperbola. So your curve will be like this. So this is the, basically we call it the low slip region. And this is the high slip region. high slip region. And this combination is called the torque slip characteristic of the three-phase induction motor. So we can say that the linear region is almost where our induction motor work. So we call it the stable region or operating region. And this high slip region where it's all unstable region, so it is called unstable. Region. So you can say that with this, the torque slip characteristic can be defined. So you can define in the low slip region and high slip regions. In low slip region, the torque is almost linear with the slip, that is T is proportional to S. And when the slip is increasing, and it will, in that case, the torque is inversely proportional to the slip actually. So it will be a rectangular hyperbola. So this is the torque slip characteristics. So in this lecture, we discuss about some basic working principle of the three-phase induction motor, the torque equation, maximum torque, starting torque, and the torque slip characteristics, which is very important as far as the examination point of view. So thank you so much for today. Thank you.